chemical bonds. So essentially our phenomenon for this one to kind of help introduce this idea to us is fluorescence. Why does a fluorescing star glow after we turn off the lights? And to understand that, we need to get down to what is happening with the atomic structure. Now there's three particles as part of an atom: protons, neutrons, and electrons. Protons and neutrons go to the center of the atom. We call that the nucleus. Now, it's very important to understand the atom nucleus is nothing like the nucleus of a cell. A nucleus of a cell has millions and millions of atoms as part of it. So we're talking about completely different scales here. Protons and neutrons in the center. Protons are positively charged and have a mass of 1. Neutrons have no charge, they're neutral, and they have a mass of 1. Electrons are not in the nucleus. Instead, they travel in shells or orbits around the atom. They do not have any, they have a negligible amount of mass. They're, I think, 1/2000th the mass of a proton. So they're way, way, way smaller. They do have equal charge. So protons and electrons, they balance each other out. Protons are positive, electrons are negative. Those two charges balance. And so that's the basic structure of the atom. Well, what happens when you charge a fluorescent star is you're adding energy. Now, not all molecules can do this. That's why fluorescent stars have to be made out of certain materials, where the energy in those special molecules gets absorbed into the electrons, and that causes the electrons move faster, right? Because they're moving faster, they're gonna need to cover a greater distance. So they get bumped out into a higher energy shell. There's up to as many, I think, 7 different shells of energy with different orbits within them. The first shell can only hold 2 electrons. The second shell can hold 8. The third shell will behave as though it's full at 8 and start filling the fourth shell. It gets a little bit more complicated. If you were in a chemistry class, you could deal with that. For a biology class, you just need to know first shell will hold 2, second shell will hold 8, third shell will act as though it's full at 8. And so that is what happens, is that as the fluorescent star absorbs that light energy and puts it into its electrons, they move out further and further away from that nucleus into higher energy levels. Then when the light is turned off, they start to drop back down into lower and lower energy levels. And as they drop down, the energy that they've lost is emitted as light. And so that's where the fluorescence comes in. All right, how to read a periodic table of elements. There's going to be a bit of information on every atomic symbol. Now, if it is a charged atom, that means it either has more protons or more electrons than, or vice versa, right? So they either have more protons or more electrons. That gives them either a positive or negative charge. If that is not noted on the symbol, you're dealing with a neutral atom. So almost all the time that you look at a symbol like this, the number of protons and electrons will be the same. The number that doesn't ever have any decimal places, it's always the smaller of the two numbers. That number represents the number of protons. And again, as I mentioned, the number of protons and electrons is almost always the same. The second number is the atomic mass. And the atomic mass is helpful to us because it helps us know how many protons and neutrons there are, because protons and neutrons are the only ones that have weight. Now, sometimes when students see this, they'll go, okay, there's 6 protons, 6 neutrons, and this must be the weight of the electron. But that's not actually the case. What we're seeing here is that almost all carbon has 6 protons and 6 neutrons to give it a mass of 12. But there are a few carbon-14 atoms. So rather than just say, all right, 98% of all carbon atoms have 6 protons, 6 neutrons, and a mass of 12. But only a very few have a mass of 14. So we're gonna just the mass at 13, that wouldn't make sense, right? So instead what we do is we do a weighted average. So it's a average weight based on the percentage of the carbon atoms that have 12 versus 14, right? And that's where we get this little decimal place here. So you'll see that as you look at atomic symbols and just round it to the nearest whole number. That's the easiest way to deal with it. Okay. If we want to identify an atom, it's all about the number of protons. We don't care about the number of neutrons or electrons when it comes to the identity of the atom. What determines its identity is the number of protons. All right. I mentioned that we could have carbon 12 or carbon 14. And in that case, because it's all carbon, they can only have 6 protons. So the difference between carbon 12 and carbon 14 is carbon 12 has 6 neutrons. Carbon 14 would have 8. Those are what we call isotopes. And isotopes can be helpful for identifying things like we learned about in our DNA. The discovery of semi-conserved DNA replication used a heavy nitrogen isotope to help do that. It also is helpful for things like nuclear power and whatnot, but not too much that we need to worry about for biology, but it can be a useful tool. And so that's where the term isotope comes from. All right, and then this was depicting the energy levels that I was talking about and how that fluorescence works. All right. Atoms, and I'm going to use, some sort of anthropomorphizing atoms, right? They don't have wants and desires, but for lack of a better way of putting it, atoms want to have a full outer shell. Whichever outer shell has electrons, so in hydrogen, this would be the outer shell with electrons, that would be the valence shell. In oxygen, the outermost shell with electrons would be now the second shell, so that would be the valence shell. All of these atoms want to have a full valence shell. So oxygen wants to get 2 more electrons to have a full outer shell. Hydrogen wants to get 1 more, because that's all it needs to get this first shell full. To do that, atoms will form bonds with other atoms. 2 or more atoms bonded together is a molecule. So that's what these atoms are trying to do, right? They're trying to get a full outer shell, and bonds are how they do that. There's a couple of different ways that can happen. The one you're seeing here is what we call a covalent bond. What's going to happen in a covalent bond is these 2 atoms, this hydrogen and this oxygen, are going to share. And there's probably some great, metaphysical understanding here, right? That comes in. When 2 atoms share electrons, each atom feels like it's gained an electron. So when hydrogen shares its electron with oxygen, hydrogen now feels like it has 2 electrons. When oxygen shares with hydrogen, it now feels like it has 7 in that outermost shell. That's why oxygen and hydrogen bond together. Now, these electrons aren't stable in a single place. They're moving around, zooming back and forth, but we're just depicting them here so we know these 2 are being shared. Now, 7 isn't enough for oxygen. They need to get to 8, and so it will form a second bond with a second hydrogen. And there we have water, H2O, forming because these 3 atoms are all trying to have a full valence shell. That is a covalent bond, and there's the sharing of electrons. This is the strongest type of bond that we're going to learn about in this class. Okay. Now, based on the angles of the bonds and the difference in what we call electronegativity. If you look, hydrogen, it likes electrons more than the others around it, but nowhere near as much as oxygen likes electrons. So that creates an imbalance where oxygen is more electronegative than hydrogen. What that means is oxygen is going to hog the electrons around it. It's going to keep those electrons over by it and only occasionally send one over to the hydrogen. If two electrons from these two different hydrogens are spending most of their time hanging around the oxygen atom, what that's going to do is create a negative charge. Now, not a full one, a partial negative charge around the oxygen end of this molecule. And over here, where they're not getting the electrons as frequently as they would like, they're going to get a slight positive charge. Just like a magnet that creates poles, right? There's a positive end and a negative end of this molecule that we call water. Now that is still a covalent bond, but because they're not sharing those electrons equally, that's a polar covalent bond, creating magnetic poles, not really magnetic, but an electrical charge on each end. And yeah, so that is going to give us a pretty unique property, because that means the next water molecule, if this end is negative and this end is positive, the next water molecule, the hydrogen end, is going to be attracted to the oxygen end over here, and they're going to come interact with one another. We'll talk more about that in a second. All right. Next can happen if we have an even greater disparity in the electronegativity of the atom, as well as some other conditions that must be met. Look at sodium here. Sodium has one electron in its outermost shell. There is just no way that atom is going to get 7 bonds to get a full valent shell. But if it can get rid of this electron, now its valent shell becomes this one, right? The outermost shell with electrons. So if it gets rid of this one, this becomes the valent shell. And that sodium now has a full valent shell just by getting rid of this electron. Look at chlorine over here. It has 7 electrons in its outermost shell. It is desperate, hungry, really wants just one more electron. And sodium's willing to give its away. Well, sodium gives that to chlorine, as is depicted here. It's going to have consequences. Sodium has lost a negative charge. It now has one more proton than electron. So it's positively charged. The chlorine gained an electron. It now has one more electron than proton. It now has a negative charge. Well, when these two things, to have that trade happen, they got to be in close proximity to each other. And now they have opposite charges. What is that sodium and chlorine going to do? Form a bond based on the electrical charges. And that is an ionic bond. Ionic bond is when there's a complete donation. So it's a little bit different than a polar covalent bond like we talked about earlier, which is still sharing. All right. There we go. Our last one here. I mentioned that the slightly negatively charged oxygen side would be attracted to the slightly positive hydrogen side of the next water molecule. And so that's where our third type of bond that we need to know comes from. Hydrogen bonds are not these bonds right here. It's not a bond between the oxygen and the hydrogen within the molecule. Instead, it's a bond between molecules, not within, but between. The partial negatively charged oxygen is going to be attracted to the partially positively charged hydrogen end of this water molecule. And that's going to form the weakest of the 3 types of bonds, this partial attraction between them. Those hydrogen bonds are what hold the middle of our DNA together. The A's, T's, G's, and C's are held together by hydrogen bonds, whereas the backbones of DNA are held together by covalent bonds, sharing, right? That's why the A's, T's, G's, and C's break apart from each other at a lower temperature because they have the weaker bond between them. And those hydrogen bonds and its attraction to charges due to the polar covalent bonds within the water molecule are what drive a lot of the unusual behavior of water molecules, why they have high surface tension, why they're attracted to charged things like this balloon, why they climb things through adhesion, which is really important to plants.